Hey guys, welcome back to the channel. Hi to all the new subscribers. We're going to be doing some fantastic stuff on Bounds later on. But first, I just want to do a quick shout out to Tilly. This is from Eva. She says, thank you for helping her out with a 3D trig. And what a fantastic example of a math scholar you are. Also, shout out to Abby. Happy birthday. I will be doing a recorder happy birthday at some point, I'm sure, on YouTube. So watch out for that. Right. So some of you have questions about the end of the last topic. I'm going to be doing a video on those later in the week. But for today, we are going to be doing bounds. Now, I normally do a list of all the different things that are covered in the lesson plan, but the topic kind of interweaves with itself quite a lot. So I haven't done a list, instead I've just done a little structure here. So bounds is to do with measure of accuracy. So you've probably already done, well, you all have done rounding to the nearest 10 or nearest 100 or 1,000 or the nearest kilometer or liter. You will obviously also be familiar with rounding to decimal places, rounding to significant figures. Something new is truncation, which you're going to look at. And all of this links up with the idea of error intervals and bounds. In terms of applications and contextual uses, things like time, area, volume, density, all that kind of stuff. If you're measuring something, you want to know how accurate you are when you're measuring it. So this video is just going to be a recap of the key skills you need before we actually go into bounds. So what I want you to do is the red number on the screen. I want you to pause the video, round it to the following significant figures, and then I'll show you the answers. Okay, so I'm going to show you the answers now. So you should have 20, 25, 25.0, the 0 is important there, 24.98 and 24.981. Okay, another thing you need to remember is how you can convert recurring decimals into fractions or even decimals, non-recurring decimals. And the idea that, for example, 0.599 recurring is equal to 0.6. So I'll do the first example for you. So if you let x equal 0.599 recurring, then you need to move the decimal so everything after the decimal matches, because then you can eliminate it by subtraction. So you're going to move it once, or in other words, multiply it by 10, and then also multiply it by 100 so that you have the nines after the decimal. When you subtract it, you get 90x is 54, and then you can divide both sides by 90 and you get 0.6. So there's your proof. I want you to now try this proof here. I'm going to pause the video and then you guys can do it and I'll show you the working out in 3 seconds. Okay, so here's the working out. It's practically the same as the previous question. You can use a calculator for this and you get 183.5. Okay, so this is the title for the topic, bounds, rounding, accuracy, and error intervals. There's one more thing you need to know before we continue here, and it is quite surprisingly basic, but I'll be referencing it later on in the topic, and that is the place value grid. So you already know the place value grid. We can represent numbers by looking at digits of a number by looking at the place value. So we know that it's going to be 10,000 down to 1, and then you got 1/10, 1/100th. You can write those as decimals as well. Obviously, it applies more to the right-hand side here. And then you can halve these numbers. Now, the reason you halve them will become apparent later on. I just need to show this to you now so I don't have to re-explain it. If you halve them, the left-hand side of the decimal is quite straightforward. The right-hand side, although you guys, I'm sure, can halve numbers like this, a common silly mistake is people will say that half of 0.1 is 0.5. So just be aware of that. So it's actually 0.05, 0.005, and so on. Okay, so looking at bounds, the basics of bounds. If a number x has been rounded to the nearest whole number to give 5, what could x have been? Or another question to answer, what's the smallest and largest values of x that could have rounded to give you 5. Now you might draw a number line to work this out, and you can say, okay, we're now rounding to the nearest whole number. So I can say the nearest whole number above and below is going to be 4 and 6. Now let's look at the left-hand side first. Well, anything such as 4.1, 4.2, 4.3, 4.4, obviously those are all going to round down to 4 if it's the nearest whole number. When you get to 4.49 and so on, that will also round down to 4. When you get to 4.5 or 4.49 recurring, if you want to be picky about that, they're technically the same numbers, you can see they round up to 5. So 4.5 is going to be the lowest number. So I'll just write that here just as a note. You don't have to write any of this out. And then the other end is going to be a bit more tricky to look at, because we're going to think about what's the upper boundary. Well, obviously numbers such as 5.1, 5.2, 5.3, they're all going to round down to 5. Now you get to a point where you have 5.5. Now that's going to round up to 6. So anything below 5.5, not including 5.5, or anything less than 5.5 is going to round down to 5. So that keyword there, or keywords less than, is crucial to the idea of bounds. We can actually write this as an inequality, and we can say that the lower bound is 4.5 and the upper bound is 5.5. And notice how I'm using the inequality signs for this. I'm not including 5.5 or 5.4999 recurring. As a matter of convenience for bounds, you can say 5.5 is the upper bound and 4.5 is the lower bound. Okay, so that's when you're rounding to the nearest whole number. Again, you can also just show it on a number line like this. You're not typically going to need to do that though in this topic. So second example, a length of 120 centimeters is measured to the nearest 10 centimeters. Find the upper and lower bound. So again, just do a number line. Now it's to the nearest 10, so I'm going to add 130 to this line, and I'm going to add 110 to this line. These are now going up in 10. Now I'm obviously going to look at numbers here and here. So that's going to be 115, and that's going to be 125. So to the nearest 10, I'm adding 5 and then I'm subtracting 5. And as an inequality, I can write it just like you can see on the screen here, 115 to 125, and those are the upper bound and the lower bound. Now, significant figures, we have to think about in a little bit more detail here. 256 is the number we're looking at. Now, the place value of the 6 is 1 unit. Obviously, the 5 is in tens and the 2 is in the hundreds column. We're not interested in the 5 or the 2, but because the 6 represents ones, it means that we can write 257 there and 256 there. So we're going to look at, well, what boundaries do we have here? Well, I'm going to half that 1, so it's going to be 256.5, and this is going to be, sorry, that should be 255.5. So there's your inequality and there's your bounds, 255.5 and 256.5. And one more example here, 0.03 rounded to one significant figure. Okay, so here's the number line again. Now the first significant figure is the first non-zero digit. In this case, it's 3. The place value of that 3 is 1/100ths, or in other words, 0.01. So if I add 0.01, I get 0.04. If I subtract it, I get 0.02. And then I need to work out what's halfway between those. So it's going to be 0.035 and 0.025. And those are your upper and lower bounds. Now, by this point, you probably have figured out a quicker method to work this out without having to draw a number line. All you really need to do is half the measure of accuracy and then add or subtract depending on whether you're finding the upper bound or lower bound. So if I just go back one slide here, if the measure of accuracy is 0.01, if I half that, I get 0.005. And you can see if I add or subtract that, I get my two values. So going back here, if I'm measuring correct to the nearest 10, well, the upper bound will be 10 divided by 2, which is 5. So I'm going to add 5 to 250, and the lower bound, I'm going to subtract 5. So I get 245 and 255. Sometimes the questions can be phrased like tenth of a millimeter. Now a tenth is just 0.1. You half that, 0.1 over 2, you get 0.05, and then you add or subtract depending on whether you're finding the upper bound or lower bound. So if I add 0.05 here, I get if I subtract, because I'm finding the lower bound, I get 422.95. If I add, I get 423.05. Okay, just do a quick spot check. I want you to work out the upper and lower bounds for A and for B, and I'm going to show you the answers in 2 seconds. Okay, so the answers for this should be 63.5 is the lower bound, 64.5 is the upper bound. And then for part B, 32.75 and 32.85. This is just a general rule. You don't have to copy this out. For those of you that are still not sure, it's just a note. So you can pause the video and read this if you want to. The rest of you probably don't need to have this slide here. Now, the next video is going to be on error intervals, followed by a worksheet. So there's no worksheet for this video so far. I'll see you in the next video.